Hi boys and girls, this video comprises the lecture for section 9.1, page 594, entitled Sequences. Basically, a sequence of numbers is an infinite succession of numbers that follow a pattern, such as 1, 2, 3, 4, etc., such as 1/2, 1/3, 1/4, etc., or possibly even an alternating pattern. Infinite succession of numbers that follow a pattern. It could be just alternating numbers. Terms in a sequence are usually denoted with a subscript. The first term of the sequence is a sub 1, the second term a sub 2, the nth term of a sequence a sub n, and so on. For example, if we're looking at the sequence of counting numbers 1, 2, 3, 4, etc., the nth term is the one that's way out there that we just generalize. We call that the nth term. Then the first term, 1 is a sub 1, the second term, 2 is a sub 2, 1 is mapped onto a sub 1, 2 is mapped onto a sub 2, and so on. The numbers a sub 1, a sub 2, a sub 3, all the way to a sub n are the terms of the sequence, and the number a sub n is the nth term of the sequence, and the entire sequence is denoted by these little brackets, a sub n. That would denote our sequence. Okay, so that's just kind of some terminology to get out of the way. Now let's list the terms of a sequence, starting with a sub n. The sequence a sub n is, this would be the nth term. Let's see what the first term would look like. A sub 1 would be 3 plus negative 1 to the 1 power. Well, negative 1 to the 1 power is negative 1. 3 minus 1 is 2. What would the second term of this sequence look like? 3 plus negative 1 quantities squared. Well, that makes this a positive 1, so a sub 2 is 4. I wonder what a sub 3 would look like. It's going to be 3 plus negative 1 cubed. Well, since negative 1 cubed is negative 1, 3 plus negative 1 is 2 again. A sub 4, 3 plus negative 1 to the 4th power. Again, negative 1 to the 4th is positive 1 plus 3 is 4. So this sequence just alternates between 2 and 4, and that is the pattern. Okay, and of course this is the general term. Now let's do letter B. B sub 1 is going to be 1 over 1 minus 2 times 1. Well, 1 minus 2 is negative 1, so this just becomes negative 1. What does the second term look like? It's going to be 2 over 1 minus 2 times 2, which is 2 over 1 minus 4, negative 3, negative 2/3. B sub 3 will be 3 over 1 minus 2 times 3. 1 minus 6 is negative 5, making this negative 3/5. And then, of course, B sub 4, just doing the first 4 terms just to give you an idea, 4 over 1 minus 2 times 4 ends up being negative 4 over 7. And those are the first 4 terms of that sequence. Let's see what the first 4 terms are of the third sequence. We have C sub 1 will be 1 squared over 2 to the 1 minus 1. Well, that's going to be 1 over 1, which is 1. C sub 2 will be 2 squared over 2 to the 2nd power minus 1. That's 4 over 4 minus 1, which is 3. C sub 3 is going to be 3 squared over 2 to the 3rd minus 1. 9 over 8 minus 1, which is 7. And C sub 4 is equal to 4 squared over 2 to the 4th minus 1, and that's going to be 16 over 16 minus 1, which is 15. So that's how you list the terms of a sequence. Not too difficult. We do have one more part to this problem, and it requires an additional definition. Recursively define sequences. Some sequences are defined recursively. To define a sequence recursively, you need to be given one or more of the first few terms. All other terms of the sequence are then defined using previous terms. Essentially, every subsequent term of the sequence is dependent upon whatever the previous term was. That's a recursively defined sequence. Therefore, we sort of need like an initial value. In this case, we're given the first term. D sub 1 is 25. Now the general term is d sub n plus 1 is d sub n minus 5. So notice that the n plus 1 term is the previous term minus 5. So d sub 2 is going to be d sub 1 minus 5. Well, d sub 1 was 25. 25 minus 5 is 20. Now d sub 3, is going to be the previous term, d sub 2 minus 5, which of course was 20. Remember, this was our d sub 2, so now we put it in here, and that's 20 minus 5, which is 15. So that's how this works. Each subsequent term is dependent upon the previous term. D sub 4 is d sub 3 minus 5. Well, d sub 3 was 15. So now we plug that in, and we get 15 minus 5 equals 10. So that's how a recursive sequence works. Now that we know how to list the terms of a sequence, let's talk about what the sequence does as n gets very large. A sub 1, 2, 3, 4, we see what those numbers are, but what happens as n approaches infinity? Well, it turns out we are primarily concerned with sequences whose terms approach limiting values. In other words, it would get closer and closer to a certain number, not necessarily just diverge randomly. Such sequences are said to converge. Very important term as we talk about sequences and series. A sequence converges to a number if, as n gets bigger, the terms get closer to a certain number. That number is the limit of the sequence. For instance, the sequence 1 over 2 to the n. Okay? When n is 1, that gives you 1/2. When n is 2, 1/4. When n is 3, 1/8. Then 1/16, 1/32. Keep going, keep going, keep going. And it turns out that we can see that this does converge to 0. Not every sequence converges, but the ones that do will have a limit. And whatever that limit is what the sequence converges to. So here is the definition of the limit of a sequence. Essentially, it's saying as n gets very large, the terms get closer and closer to a certain value. But notice here it says if the limit L of a sequence exists, then the sequence converges to that number. It's kind of like a horizontal asymptote sort of thing. When we know that the limit of a function is a certain number, it's approaching a certain value, generally that's a horizontal asymptote. Similar here. If the limit of a sequence does not exist, then the sequence diverges. Now you might be thinking, well, what would that look like? There are different ways in which a sequence can fail to have a limit. If the terms of a sequence increase or decrease without bound, symbolically, these cases are written as follows. Pretend like there's an A here. I see my little typo. Terms increase without bound. That means as n gets very large, the limit of the sequence is approaching positive infinity. And if the terms decrease without bound, then the limit as n approaches infinity, the terms approach negative infinity. So if the limit is infinity or negative infinity, we have a divergent sequence. Okay. Now let's determine whether a sequence converges or diverges. The way to do that, since we can't actually list all of the terms and see what's happening over there as n gets close to infinity, we have to look at the general term of the sequence and see what the limit would be there. In fact, let's go back to this example. The general term of this sequence that I have listed here, 1/2, 1/4, 1/8, etc., is 1 over 2 to the n. That describes each term in the sequence as n is 1, n is 2, n is 3. We would say the general term then is 1 over 2 to the n power. Well, we can look at 1 over 2 to the n power to determine if the sequence converges or diverges by taking the limit as n gets very large of 1 over 2 to the n. Remember, plugging infinity into the denominator is going to give us 1 over infinity, which is 0. which tells us that this sequence does have a limit. That limit is 0, and therefore that sequence converges to 0. So notice how we focused on the general term of the sequence in order to discover what was happening with the sequence in general. Now, that's what we're going to do here as well. However, we're not going to take the limit of this sequence because we remember this was what we had in the first example. The terms of this sequence were 2, 4, 2, 4. It keeps going like that, right? Continuously. We can see that since this is alternating between 2 and 4, it's not going to converge to one specific number, so this sequence diverges. But for this general term, let's go ahead and take the limit. The limit as n approaches infinity of n over 1 minus 2n. Well, plugging infinity in here gives us something that we can't really quantify. So we're going to use that little trick that we learned where we divide each of the term by the variable with the highest exponent. In this case, that is, of course, n to the 1. So let's divide each term in this rational function by n. This is going to be 1 over n minus 2n over n. This is just a way, of rewriting this rational function. We're going to now have 1 over n minus 2. Now let's take the limit as n approaches infinity. Notice we've kind of solved our problem because 1 over n here gives us 1 over infinity 0. This becomes 1 over 0 minus 2, which is negative 1/2. This sequence has a limit of negative 1/2. Therefore, it converges to negative 1/2. Okay, we can also, you may have thought in the previous example, hey, I wonder if we can use L'Hopital's rule to find the limit. Why? Yes, you can. Using L'Hopital's rule to determine convergence. Show that the sequence whose nth term is a sub n equals n squared over 2n minus 1, see if it converges. Well, let's take the limit. Remember, we're interested in what's happening when n gets very large as it approaches infinity. Of this function, n squared over 2 to the n minus 1. Plugging infinity in directly gives us infinity over infinity, which, as you know, is an indeterminate form. So let's use L'Hopital's rule. We're going to take the derivative of the numerator and the derivative of the denominator. You may have forgotten how to take the derivative of something like 2 to the n, but you can look that up or revisit. It turns out that's going to be natural log of 2, 2 to the n power. Now let's try to take the limit as n approaches infinity. Notice we get infinity over infinity again. How about L'Hopitaling again? We're going to take the limit of the numerator, the derivative of the numerator, which is 2, over the derivative of the denominator, which is now natural log of 2 again, which makes it natural log of 2 squared, 2 to the n. When we take the limit as n approaches infinity in this case, we get 2 over infinity, which is 0. Therefore, the limit of this sequence is 0, and it converges to 0. The terms get closer and closer to 0, and that is also its limit. All right. Now let's switch gears a little bit here and realize that we can also look at a sequence that doesn't already give us the general term and find a pattern in order to determine what that general term is. So this leads us to pattern recognition for sequences. Sometimes the terms of a sequence are generated by a rule that does not explicitly identify the nth term. We might have to do that. In such cases, you may be required to discover a pattern in the sequence to describe the nth term. Once the nth term has been specified, you can investigate the convergence or divergence of the sequence. For example, remember that example that we had initially where it was 1 over 1 and then 1 over 2. I think it actually started with 1 over 2. And then 1 over 4, and then 1 over 8, and then 1 over 16. We may have looked at this pattern and said, wait a minute, this is 2 to the 1, 2 squared, 2 cubed. 2 to the 4th power. And of course the numerator is always 1. So this general term is a 1 over 2 to the n. That's how you can look at the pattern of the terms and try to describe the pattern and generate your own nth term. Then once you find it, you can determine whether the sequence diverges or converges. Now, since I'm not sure if you've seen factorials before, it turns out that a useful way of simplifying some of the formulas that you developed is to use factorials. For example, just to define what it is, 7 factorial is 7 times 6 times 5 times 4 times 3 times 2 times 1. So you may see a pattern, whatever that number is, 7 times whatever, blah, 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 blah. You could say, well, that's 7 factorial, and then maybe you can see a pattern where maybe it's 1 factorial, 2 factorial, etc. By definition, it's going to be 0 factorial is equal to 1. Similar to when we say anything to the 0 power is 1 by definition, 0 factorial is 1 by definition as well. I think I need to switch colors here. So on example 6, page 598, let's find the nth term of a sequence by trying to figure out the pattern of numbers that we see here. Now for the numerators, it seems like I've got 2 to the 1, then 2 squared, then 2 cubed, 2 to the 4th, 2 to the 5th power. That seems like the rule, doesn't it? Therefore, in my nth term, I'll say 2 to the n power, where n is 1, 2, 3, 4, 5, etc. In the denominator, it looks like I just have odd numbers, 1, 3, 5, 7, 9. I would guess the next one would be 11 or whatever. It turns out that the way that you quantify odd numbers is to say 2n, which makes it even, and then subtract 1. So when n is equal to 1, 2 times 1 is 2, minus 1, 1. When n is equal to 2, 2 times 2 is 4, minus 1, 3. 2 times 3 is 6, minus 1, 5. So this is the nth term of our sequence. It describes as n equals 1, then 2, then 3, then 4, etc., each of the terms of the sequence that we see here. But we had to discover the pattern. Now, to be honest, describing a pattern of a sequence and finding the nth term takes some experience, some skill, a little bit of artistry and creativity. You see me do this thinking, good grief, I could spend a lot of time on this trying to figure it out. Well, the more of these you do, the better you will be at recognizing the patterns and generating the nth term. But now that we have it, let's see if our sequence diverges or converges. So let's take the limit as n approaches infinity of 2 to the n over 2n minus 1. Plugging this in directly gives us infinity over infinity. Since that's an indeterminate form, we can use L'Hopital's rule, which will give us the natural log of 2 to the n, over 2. Now when we take the limit as n approaches infinity, we get infinity over 2, which is infinity, boys and girls, meaning that this particular sequence diverges. We did not see it converging to a limit, and therefore there is no point that it's converging to. Now let's do one more example, and then we'll be done with this lecture. For example 7, we're going to look at these helpful tips for determining the nth term. If you want to express a pattern of odd integers, use 2n minus 1 or 2n plus 1. 2n makes it even, subtracting 1 or adding 1 takes you to an odd number. So that's a great way to describe odd numbers. To express even numbers, 2n. Obviously, just multiplying a number by 2 is going to make it even. And if the terms alternate in sign, this handy little coefficient will change the sign from negative to positive, because negative 1 to the 1, of course, is negative 1, but negative 1 squared, positive 1. Negative 1 cubed, negative 1. Negative 1 to the 4th, positive 1. So attaching that to your general term will alternate the signs. And we're going to need that here. Notice that we have a negative, then a positive, then a negative, then a positive. So these terms alternate. Therefore, our nth term needs to alternate, and we'll just use -1 to the n power as the coefficient so that we can make the signs alternate. Now, as far as the numerator is concerned, you could spend some time trying to figure this out. This looks like 2 to the 1 and then 2 cubed, but then this isn't a power of 2 and this isn't a power of 2. But you might begin to recognize, wait a minute, let me look at powers of 3. 3 to the 1, of course, is 3. 3 squared is 9. 3 cubed is 27. 3 to the 4th power is 81. This is 1 less than each of the powers of 3. So the numerator can be quantified this way. 3 to the n, but then subtract 1 from it. So raise 3 to the first power, second power, third power, but in each case subtract 1, and that gives us the numerators that we have here. Now the denominator is going to be factorials. Since you're not as familiar with factorials, you might not recognize that, but 1 factorial is 1, of course, and then 2 factorial is 2 times 1, which is 2. 3 factorial is 3 times 2 times 1, which is 6. 4 factorial is going to be 4 times 3 times 2 times 1. You kind of get the idea here, which is 24. 5 factorial is 5 times 24, which is 120. And so after you've seen factorials for a while, you would begin to recognize, oh, that's just factorials, n factorial. So there is your nth term. Again, takes a little skill, experience, artistry, creativity, perhaps a little luck as well, but you learn to recognize the patterns and describe the sequence. That's it for this lecture. Here's your homework assignment. It's page 602. 6, 12, 24, 27, 35, 38, 46, 51, 59, 60, 62, 76, 78, 82. And the next time you're playing rock, paper, scissors, lizard, Spock, you will know what the rules are, boys and girls. And that's it for today.